Hi everyone. In this presentation, I am going to discuss as to how to obtain the half-range Fourier series expansion of a function f of x, which is defined in the interval 0, L. Before that, we'll quickly revisit the Fourier series expansion of a function f of x. So as we all know, the Fourier series expansion of a function f of x, which is defined in the interval alpha comma alpha plus 2l, is given by this expression f of x equals a naught by 2 plus summation n equals 1 to infinity a n cos n pi x by l plus summation b n sin n pi x by l, where a naught is given by 1 by l integral alpha to alpha plus 2l f of x dx, a n is given by 1 by l integral alpha to alpha plus 2l f of x cos n pi x by l dx, and b n equals 1 by l integral alpha to alpha plus 2l f of x sin n pi x by l dx. So this expression, as you can see in the right hand side, is what is known as the Fourier series expansion of f of x. Of course, if f of x satisfies the Dirichlet's conditions in the interval alpha comma alpha plus 2l, then this function f of x converges to the Fourier series expansion. And as I said, these coefficients a naught, a n and b n are also called as the Euler's coefficients, and they are given by these expressions, right? So this is exactly how we obtain the Fourier series expansion of a given function. And of course, we also know that if the given function f of x is an even function, say in the interval say minus l comma l, then it so happens that the value of bn turns out to be 0, because f of x is going to be even, and sine function, as we know, is an odd function. The product of both, which would give us an odd function, so that bn becomes 0, and accordingly a naught and an will not be 0, and they will be given by 2 by l integral alpha 0 to l f of x dx, and an will be 2 by l integral 0 to l f of x cos n pi x by l dx. So effectively, if you have f of x to be an even function, you see that f of x will be in terms of only a naught and an's, so that there will be no sine terms in the Fourier series expansion. Likewise, if f of x turns out to be an odd function, correspondingly we are going to see that a naught and an become 0, because f of x is odd, and f of x into cos n pi x by l will also be odd, so that a naught and an become 0, and the Fourier series expansion of f of x will contain only sine terms, right? I hope all of you can recall these things, because the rest of the discussion will be based on what we have discussed just now, right? So keeping these in mind, now we'll start seeing as to what exactly we mean by the half range series expansion of a given function f of x. So as discussed just now, if f of x is odd, it so happens that the Fourier series contains only sine terms, and if f of x is even, then the Fourier series contains only cosine terms. However, if the given function is neither odd nor even, then its Fourier series expansion may contain both sine and cosine terms, right? Now the question comes as to what should be done, or what could be done, if we need to have the Fourier series expansion of a given function which is neither odd nor even, to have only cosine terms or only sine terms. And the answer to that is to construct something called the half range series expansion of the given function. So to begin with, the function of consideration is f of x, right? So we have f of x, which is now defined not in the interval alpha comma alpha plus 2l, but in the interval 0 comma l. Okay, so we are given a function f of x which is defined in the interval 0 comma l. So this is the given function of consideration, and as I said, suppose we wish to have the Fourier series expansion of f of x in such a way that it it means the Fourier series contains only cosine terms as such. So we assume that f of x is going to satisfy the Dirichlet's conditions, and now we are supposed to have the Fourier series expansion of f of x in such a way that it contains only cosine terms. Then what exactly we are going to do is that then we extend the given function f of x. It is actually, as you can see, is defined in the interval 0 comma l, but we extend it to the interval and now what we'll do is we'll extend the function to the interval minus l comma l. Okay, and because we are extending it to a new interval minus l comma l, we have the liberty to define the function in the other part of the new interval, which is from minus l to 0. So we extend f of x to the interval minus l comma l so that the new function becomes an even function in minus l comma l. Okay, so what exactly we are doing is that we will construct the new function or extend the new function f of x to the interval. In fact, f of x is a given function and we are going to extend it to the new interval minus l comma l in such a way that the new function becomes an even function in minus l comma l. Right? So if this is done, what will happen? Then the Fourier series expansion of f of x in minus l comma l, one second, yeah, so now the actual interval that is given is 0 comma l, and that is where f of x is defined. But now if we try expanding this function f of x in minus l comma l, it so happens that, yeah, what will happen to the expansion of the given function? So we will have the same expression as it is initially. Okay, so this will be the Fourier series expansion. But now because f of x has become an even function in minus l comma l, what will happen? Because f of x becomes an even function, it so happens that bn turns out to be 0, because f of x is even and sine function is odd, so that the product is an odd function. So bn becomes 0, so there will be no bn term as such. Sorry, second. Yeah, so the bn term will vanish as such because bn is becoming 0, and now the interval of consideration for a0 and an would be integral minus l to l, and because f of x is an even function, the expression for a0 will change to 2 by l integral minus l to l f of x dx, right? And similarly for an, once again the interval would be, yeah, one second, sorry, initially it is minus l to l. Because the given function becomes even, we're going to get the integral as integral 0 to l. So once again here initially, one second, yeah, initially the interval of consideration for a0 and an both will be from minus L to L, correct? But because f of x is an even function, we're going to see that this integral will change to, sorry, integral, sorry, 2 by L integral 0 to L f of x cos n by x by L dx. Okay, so this is going to be the Fourier series expansion of f of x in the interval minus L comma L. But because we have the original function to be defined in 0 comma L, this expansion will remain the same, and this will be called the half range series expansion. This Fourier expansion is called the half range cosine series expansion of f of x in the interval of f of x in the interval minus L, in the interval 0 comma L. Why 0 comma L? It is because the original function is defined in 0 comma L. And very importantly, this expansion that we have is convergent for all values of x in the interval 0 comma L. So what I'm trying to say is that this expansion, as you can see here, will be convergent for all values of x which are taken in the interval 0 comma L. Why is this happening? Because the original function that is given is defined only in the interval 0 comma L. So to summarize, what exactly we are doing here is that even though the given function is defined in the interval 0 comma L, we extend it to a new function in the interval minus L comma L and make it an even function, so that its Fourier series expansion will have only f of x in terms of a0 and an. Very importantly, bn vanishes, so the series will contain only cosine terms, and this series expansion is called the half range cosine series expansion of f of x, and is valid only for all values of x in the interval 0 comma L. Very importantly, this Fourier series expansion will not be valid for any value of x outside the interval 0 comma L, that is particularly in the interval minus L comma 0, because in the interval minus L comma 0 we have simply redefined the function in such a way that it becomes an even function. So to put things together, this expression what we have got here is what has to be remembered as the Fourier series expansion, the half range cosine series expansion precisely of f of x. So what exactly are we supposed to do? We will simply have to write f of x in terms of a0 and an, and particularly a0 and an correspondingly are defined only in the interval 0 comma L. So we are going to get a0 as 2 by L integral 0 to L f of x dx, and an to be 2 by L integral 0 to L f of x cos n by x by L dx. So this is what is called the half range cosine series expansion. Now similarly we have, this is supposed to be half range cosine series as discussed just now. Okay, so similarly we have something called the half range sine series expansion. So we'll understand as to what exactly is happening with that now. Okay, so first of all, what do you mean by, or how do you get the half range sine series expansion? Once again, the given function is defined in the interval 0 comma L, but now we would like to expand the given function as a Fourier series such that it contains only sine terms. Okay, so instead of having only cosine terms, we try to get only sine terms, and for that to happen, we extend the function once again to the interval 0 minus l comma l, but now we'll ensure that the new function turns out to be an odd function in minus l comma l. And what will happen if the function becomes an odd function? Obviously, now the Fourier series expansion will not have a0 and an. Instead, it will have only bn. Why? It is because when you go for a0, initially, as we know, the expression for a0 would be integral 1 by l integral minus l to l f of x dx, and this effectively becomes 0 because f of x is an odd function in minus l comma l. So obviously there is no need to retain the expression for a0, and similarly an also becomes 0. So instead of a0 and an, we'll be having only bn. And what will be the expression for bn? So initially it is 1 by l integral minus l to l f of x sine n pi x by dx. But because f of x is an odd function and sine function is also an odd function, the product of these two becomes an even function, and accordingly the integral turns out to be 2 by l integral 0 to l f of x sine n pi x by l dx. Right? Now this expansion that we have got here is called the half range sine series expansion of f of x defined in the interval 0 comma l, and once again is convergent for all values of x in the interval 0 comma l. Right? So this is what is known as the half range sine series expansion of the given function. Right? So these are the two particular half range series expansions of any function f of x. So one is called the half range cosine series, and the other one is called the half range sine series. And of course, if you have really understood this well, it is supposed to be obvious that even though the function is the same, we can have both the half range cosine series and the half range sine series of the given function defined in the interval 0 comma l. So for if you are told to find the half range cosine series, you convert the function into an even function, and accordingly the Fourier series will have only a0 and an, right? And the corresponding a0 and an are given by these two expressions. And if you are told to find the half range sine series expansion, you have it in terms of only bn, and bn is given by this expression. Right? This is exactly what has to be done when it comes to problems. Okay, so now that I've explained this particular concept, I will work out a simple problem for you to understand things in a much better way. Okay, so the problem of consideration would be this: expand f of x. I'm going to define f of x to be, say, pi minus x. Okay, so this is how I'm taking a function as such. Expand f of x as a half range sine series in the interval say the interval, suppose we take it as 0 comma pi. Okay, so a typical question on a half range sine series expansion or cosine series expansion will be in this form. So we'll be given a function, and very importantly the interval that would be given would be of the form 0 comma l as such. Okay, now we'll see how to do this. So to begin with, as we can see here, f of x is defined to be pi minus x. We already are given with this, and now comparing the given interval with the general interval 0 comma L, we see that L turns out to be pi. I repeat once again, whether it is half range sine series or cosine series, the interval of consideration must be of the form 0 comma L. So very easily you can see that L is going to be pi. So because L is pi and we are told to find the half range sine series expansion, as I have written earlier, f of x is supposed to be summation n equals 1 to infinity. Remember, if it is the sine series, we'll have only bn. So this will be f of x equals summation bn sine n by x by L, where yeah, here we are supposed to know what bn is. So as written earlier, bn is equal to 2 by L integral 0 to L f of x sine n by x by L dx. Right? So now, because we know that L is going to be pi, the whole expression turns out to be f of x equals summation n equals 1 to infinity bn sine, because L is nothing but pi, this turns out to be simply sine nx. Right? So this is sine nx, and here we'll have to find the value of bn. So what will be bn? Bn equals, now because L is pi, this is 2 by pi integral 0 to pi, and now f of x, as we can see here, is pi minus x, so this will be pi minus x, and then sine, once again because L is pi, this will just be sine nx dx. Right? Now the rest of the solution of the problem lies in integrating this function pi minus x into sine nx, and of course I would simply go for Bernoulli's rule. So using Bernoulli's rule, I see that the first term would be pi minus x into integration of sine x is cos x, so this will be minus cos nx whole divided by n. Correct? So this is going to be the first term as such. Okay, and then we take a minus sign, and then differentiation of pi minus x is going to be minus 1. Okay, and integration of minus cos nx is minus sine nx divided by n square. Right? And when we go for the next term, because this is a constant, the differentiation of this will become 0, so we will have the next term to be 0, and accordingly all the subsequent terms become 0. So we'll just have to take the limits for this. Now before I take the limits, I would like to see if any of these terms becomes 0. Okay, so as you can see here, because we have a sine function, when you go for the upper limit, sine n pi is going to become 0. So accordingly the upper limit becomes 0. I'm marking it this way here. And when you go for the lower limit, sine 0 is again 0. So this again is 0. So as such, this whole term vanishes. And for this term, when you take the upper limit, pi minus pi will give you 0, and 0 into any finite number is 0. So once again here, the upper limit becomes 0. For the upper limit, the term will become 0. When you go for the lower limit, when you take x equal to 0, you get pi here, and cos 0 is what you get here, and both are non-zero, so you are going to get the lower limit term only. So from this you can see that we are going to get only the lower limit term pertaining to the first term. So we get a 0 minus, because it's lower limit term. Now when you take x equal to 0, you see that this would be pi into, yeah, what do you get here? Minus cos 0 is going to be 1, right? And this will be minus 1 by n as such. So upon simplification, this will turn out to be simply 2 divided by n. Correct? So this is what is Bn, and once we have got the Bn, we would simply conclude that the half range sine series of the given function is, yeah, what will this be? As we have written here, f of x is simply sigma bn sin nx. So accordingly, now this will turn out to be f of x, and because it's a single function, I can also replace it by the given function itself. So this is pi minus x, and this will be summation n equals 1 to infinity, and bn, as we have seen earlier, is 2 by n. So this will be 2 divided by n into sine nx. So this will be the required half range sine series expansion of the given function. Okay. Now I would like to work out one more problem wherein I'll explain as to how to expand or how to obtain the half range cosine series expansion. So I would like to take up this problem. So question, I'm going to modify it a little further. So, obtain the half range cosine series expansion of f of x equals, say, suppose we are given f of x to be something like this. Just 1 minute, I'll write it down for you here. So suppose f of x is defined to be 1 for 0 less than x less than 1, and it is defined as x for 1 less than x less than 2. So suppose this is a given function and we are told to find the half range cosine series expansion of this function. Okay, so how do you go about this? Yes, so first of all, f of x is given to be this, that is obviously given. Now when you have to find out alpha, no sorry, there's no alpha here, you will have to find out L. For you to find out L, you will have to compare the interval, the general interval 0 comma L. So now the interval of consideration in this problem is 0 to 0 comma 2. So L is going to be 2. Okay, now because L is 2, now we will write the formulae first. So the half range cosine series expansion of f of x is given by, I'll just borrow this expression straight away because I do not want to spend too much of time typing this as such. Okay, so I'll just write down this expression straight away here. So this is going to be the Fourier series expansion, half range cosine series expansion, sorry. So yeah, so this is what is supposed to be f of x, a naught by 2 plus summation a n cos n pi x by L, where a naught is 2 by L integral 0 to L f of x dx, and a n is 2 by L integral 0 to L f of x cos n pi x by L dx. Okay, so accordingly, now we will start finding a naught. So a naught as given above is 2 by, yeah, what is L here? It is L is 2 here, as you can see. So because L is 2, this will be 2 by 2, which is 1. So this is simply integral 0 to 2 f of x dx. And because f of x is a split function, we'll have to split this in terms of two integrals. So integral 0 to 1, and between 0 and 1 the function is 1, so this will simply be 1 dx. The second integral will be from 1 to 2, and for this we'll have to take f of x as x, right? Upon integration, this will be, the first integral will be x, and when you go for the limits, it will give you the upper limit as 1 and the lower limit as 0, right? And for the second term, this will be x square by 2 upon integration, and so when you go for the limits, this would be 2 square upper limit and 1 square lower limit, so effectively I think this will be 3 by 2. So the value of a naught is going to be 5 by 2. I have hurried a little in this expression, so forgive me if I am wrong with this number as such. Now we'll go for an. So once again, because L is 2, this will simply be integral 0 to 2 f of x cos, and now because L is 2, this will be cos n pi x by 2 dx, correct? And once again, because the given f of x is a split function, from 0 to 1 f of x will be 1, so this will simply be integral 0 to 1 cos n pi x by 2 dx, and from 1 to 2 f of x is going to be x, so this will be x into cos n pi x by 2 dx, right? Now integration of the first term will simply be minus sine n pi x by 2 from 0 to 1 as such, and for the second term you will have to go for Bernoulli's rule here again, so this will be x into sine n pi x by 2 whole divided by n pi by 2, correct? So this is the first term, and for the second term this will be minus, when you go for differentiation of x it will be 1, and when you integrate sine function this will give you a cos function, so this minus cos function, sorry, so this will be plus cos n pi x by 2 divided by n square pi square by 4, and for this the limits will be from 1 to 2. Okay, now once again if I check as to what all terms will vanish, so when you go for the upper limit for this, even though this is a sine function, you get sine n pi by 2 because x is going to be 1, and that is definitely not 0, so the upper limit will not become 0. But when you go for the lower limit, when you take x as 0, sine 0 would be 0, so this will have its lower limit to be 0. And in this term, again, when you go for the upper limit, sine n pi is what you get here because x is 2, so the upper limit for this term will be 0, and the lower limit for this term will not be 0 because you get sine n pi by 2. And this is cosine function, because this is a cosine function, neither the upper limit nor the lower limit will be 0 for this. Okay, so accordingly, now because the upper limit is non-zero, this will be minus sine n pi by 2, correct? And when we come to this expression, in this, for the first term, the upper limit is 0, so I will simply write as 0. And for the lower limit, I choose x as 1, so this will be x becoming 1, so just 1, and then sine n n pi by 2 divided by n pi by 2, correct? So this is what we have for the first term. And for the second term, when you go for the upper limit, you get cos n pi. Cos n pi, as we know, is minus 1 power n. And for the lower limit, you get cos n pi by 2, because x is 1. So this will have the common denominator as n square pi square by 4. So this will be the expression for an. Of course, you can simplify this a little further if time permits. Otherwise, you can just leave the expression for an as it is. And we've already got a naught to be 5 by 2, as you can see here. Okay, so the rest would be to substitute a naught and an in this expression for f of x, and that will be the half range cosine series expansion of f of x, right? So this is exactly how you have to go for the half range sine series expansion and half range cosine series expansion of f of x, which is defined in the interval 0, L. Yeah, particularly in the examination, obviously, if you observe carefully, obtaining the Fourier series expansion of a given function generally is more tedious compared to finding the half range series as such. Particularly when it comes to finding the half range cosine series and half range sine series, finding half range sine series is much easier compared to half range cosine series, because if you are told to find the half range sine series, you will just have to find out bn. But if it is half range cosine series, you will have to find out both a naught and en. So that way, when it comes to the examination, I think you should be able to see that solving a problem involving a half range series is going to be much easier compared to solving a problem where you will have to find out the general Fourier series expansion, right? So pick the problems wisely and solve them accordingly is what I would suggest you all. Okay, so with this, I'm going to end with this session. So prepare well for the examination. All the very best. See you soon.